Hey YouTube, how's it going? YakScience here with another OChem video. The topic today is going to be nucleophilicity and solvents. So what is nucleophilicity? Nucleophilicity basically refers to how well a nucleophile could do its job. And remember we said in the previous video that a nucleophile is just a source of electrons and it acts as a Lewis base by donating those electrons to some electron deficient source, like an electrophile. And when we're considering how strong a nucleophile is or how well it could do its job, we need to consider the solvent that it's in. In other words, is it in methanol? Is it in water? Is it in acetone? And depending on the solvent that it's in, the nucleophile will behave differently and have different strengths. So you can't just say this is a strong nucleophile, this is a weak nucleophile. You have to consider what solvent it's in. Okay? So there are two basic types of solvent that you're typically responsible for: polar protic and polar aprotic. So let's write those down real quick. Alright, so two columns, polar protic and polar aprotic. So what is a polar protic solvent? A polar protic solvent contains polar bonds, of course, but the protic part comes from the word proton. Essentially, it's a solvent that has acidic hydrogens or hydrogens that can hydrogen bond with the nucleophile. For instance, water, right? If we look at water, notice that the oxygen is electronegative, it gets a delta minus charge, and each of these hydrogens gets a delta positive charge. And what that means is that these hydrogens can interact through hydrogen bonds with a negatively charged nucleophile. Polar aprotic, on the other hand, substances like acetone, right? If we look at the structure of acetone, right, there are 3 hydrogens here and 3 hydrogens here, but they will not be parts of any hydrogen bonding because they are carbon-hydrogen bonds, which are non-polar, right? Another example could be diethyl ether, right? Something like that. Again, you have a bunch of hydrogens, but none of them are going to participate in hydrogen bonding. So now that we know the basic definition of these two, let's talk about each one and how it affects nucleophilicity. So first, starting off with polar protic, let's take a nucleophile like F-, fluoride ion, okay? Now we know that fluoride ion is a very small atom compared to the other halogens, right? It is, or halides. It is the smallest halide. And what would happen if we put this in a polar protic solvent like water or any alcohol? All of those are polar protic. Let's just do water for simplicity. Well, what will happen is this. Remember, water has 2 hydrogens that are delta positive and an oxygen that's delta negative. So the hydrogens that are delta positive will start surrounding this fluorine and forming a hydration shell, right? Because those hydrogens are delta plus, they're attracted to that negative charge. So you get a bunch of hydrogens, a bunch of water molecules surrounding this fluoride and forming a hydration shell. Okay? And what this means is it'll hinder the nucleophilicity of F- a great deal, especially because F- is so small, and these polar protic water molecules will surround it, form that hydration shell. It will really prevent this from attacking an electrophile. Okay? But then, if we look at a different halide, like let's say iodide, which is much, much, much bigger than fluoride, let's just draw that bigger. So iodide, then yes, you will still get a hydration shell around it, but because it's so big, the hydration shell will not have as big an effect, right? It can still do its job because it's much more polarizable, it's much bigger, and just overall its nucleophilicity is not hindered as much, okay? So both fluoride and iodide would have a hydration shell, sure, or if it were alcohol, the alcohol hydrogens would surround it, definitely. But the iodide, the point to take home is iodide is less affected than fluoride. So what's the trend? What's the trend that we see going on here? In polar protic solvents, it seems to be that size is the major issue. Because iodide, I-, is a better nucleophile than bromide, which is a better nucleophile than chloride, which is a better nucleophile than fluoride, right? So in polar protic solvents, the culprit, right, the main thing to consider is size, because the bigger atoms are less affected by the hydration shell if it's water, or just the surrounding hydrogen bonding, okay? Moving on to polar aprotic, again, that means that the solvent lacks hydrogens that can hydrogen bond with the nucleophile. So let's go through the same example again. Let's look at F minus. F minus we know is a much stronger base than I minus, right? And we could do that intuitively by asking ourselves what is the stronger acid, HI or HF, and the answer is HI. And we know that the conjugate base of a strong acid is weak. So that means that I minus is a much weaker base than F minus. So since we don't have those hydrogen bonds to surround the F minus because the polar aprotic lacks those hydrogens, we don't have to worry about size as much. Instead, the main culprit here is basicity. And when the main culprit is basicity, this whole trend is completely reversed. So now all of a sudden in a polar aprotic solvent, F minus is the strongest nucleophile of the halogens, of the halides, followed by chloride, followed by bromide, and followed by iodide. Okay? So the point to take home when you're in polar aprotic solvents, size. Size is the main thing to consider. When you're in polar aprotic, basicity is the main culprit, right? How basic something is. And you can figure that out just by looking at its conjugate acid. Okay, so that's nucleophilicity and solvents. I hope that helped. Thanks for watching.